Okay, let's do another practice exam. Woo! Because why? Well, the more we do, the more confident we get, and the better prepared we'll be. But actually, this is a fantastic practice exam to do. And, I shouldn't have favorite practice exams. And I'm not saying that any one practice exam is the best, but in some sense, this is going to be the one closest to what you'll see on the test. So, why do I say that? At least it's going to be the closest in terms of the formatting. And so when you look at this, you're like, oh, yeah, this feels like what an exam should feel like. And so let's take our time, make sure we understand what's going on. And so we'll go in confident and prepared. All right, so what are some things we should make some notes of? Well, one of the things is that the instructions you see here are exactly the instructions that will be on the exam. And of course, we'll draw attention to say, oh, there's a table of Laplace transforms attached to this exam for the reference. And so we can go to the last page, and there it is. We probably won't need that until a while. We'll put that aside. And so, but, same old, right? Turn off your cell phones, clear off your desk. Calculator's not allowed. That's all right. We don't need calculators. We can do this. So let's write our name. We'll say that our name today is solutions. And let's get going. All right. Number 1. Find a general solution to the non-homogeneous equation y double prime plus 4y equals sine of 2x. Now, there's a dead giveaway to what we need to do on this problem. It says the word non-homogeneous. Now, even if it didn't say the word, we would know that it's non-homogeneous because we can see right there that sine of 2x is saying, whoa, there's something on that other side. Pay attention. And so when we see non-homogeneous, there's only 2 options available from what the material has been since the last exam, which means it's either method of undetermined coefficients or variation of parameters. Now, which one? Now, variation of parameters always works, but method of undetermined coefficients is oftentimes easier for us to understand and run through. You just have to make sure that the right-hand side is nice, and it is. In other words, it's something that we would expect to show up as a solution to a homogeneous differential equation, and the equation itself only involves constant coefficients, and it does. So, all right, good news for us. Now, how do we run through it? Well, we start by saying, what's the homogeneous problem? And for that, well, we're going to have y double prime plus 4y equals 0. We turn this into a polynomial. R squared plus 4 equals 0. And that means that our roots are plus minus 2i. So that tells us that our homogeneous solution, we'll call that our complementary solution, y sub c, has the following form. Well, 2i means it looks like some constant sine of 2x. See, we should know here our variables are x, our function is y. So some constant sine of 2x plus some other constant cosine of 2x. All right, great. No worries. So now that we have our homogeneous part, next part is what's the right form, right? Because that's how we proceed with method of undetermined coefficients. We say, what should our answer look like? And it's not too hard to figure that out. Because what you do is you go to that right-hand side, say, okay, that's our key. That's what we're going to go off of. And we start by saying, okay, we have sine of 2x showing up. Now there's a couple of rules. If there's a sine, there has to be a cosine pair. Okay, so we also have cosine 2x showing up. And if we have like a power of x in front, we have to go lower powers. Okay, that's not happening here. The other thing we have to keep in mind is the potential for the need to bump. Now, how do we know? what we look at is, do we say, is there overlap between the functions we need and what's in our homogeneous? And in this case, yeah, there kind of is. And if there is that overlap, we say, okay, bump up. And here, by bumping, we mean multiply by powers of x. So our particular solution is going to be some combination of those two functions. So we write yp is some constant a times x sine 2x plus some constant b x cosine 2x. Now comes the long part. And the long part of this is getting this part right there, y double prime. And it's just a matter of being very careful in computing derivatives. So no rush, we've got plenty of time. Start by taking the first derivative. And so we're going to use the product rule. So we're going to get a sine of 2x, the root of the first, times the second, plus 2a cosine 2x, right? And then that's times x, because I forgot to write down the first. The root of the second, sine 2x is 2 cosine 2x. Then b cosine 2x minus 2b x sine of 2x. And you can tell I'm paying attention because I had 2b and I didn't even make the joke. Wow, Steve's being serious. Oh! Okay, that's the first derivative. Second derivative. So yp double prime. And this might take a bit of space, but that's okay. We have time. We have space. All right, so we'll have a times 2 cosine 2x. All right, that's good. And here, well, I can take the derivative of x. So that would be 2a cosine 2x. And then now, if I take the derivative of the cosine, well, that would be minus, the 2 comes out. So it would be 4ax sine of 2x. That's the first two terms. And, well, okay, I'll start the next line. Derivative of b cosine 2x will be minus 2b sine 2x. Then take here, product rule, derivative of the first, minus 2b sine 2x. And derivative of the second will give us a cosine coming out. And so we will get minus 4bx cosine 2x. Okay. Now, that was the hard part. We could rewrite this because we can combine the two terms there, the two terms there. So this is the same as 4a cosine 2x minus 4ax sine of 2x. And then we have minus 4b sine of 2x and minus 4bx cosine 2x. All right. Well, the next part, and we can tell that we're transitioning here because I'm going to a new color, is to say, okay, now that we have our second derivative and the function, we're going to plug it into there. So we know sine of 2x, that's equal to yp double prime plus 4yp. All right. And, well, now we say, look, we know what yp double prime is, and we can take 4yp. So this would be equal to, we'll have 4a cosine 2x and minus 4ax sine of 2x minus 4b sine of 2x. I'll just keep going on the next line. Minus 4bx cosine 2x. Okay, that's the yp double prime. 4yp, so I'm just going to multiply everything by 4. Plus 4ax sine of 2x. plus 4bx cosine 2x. And now we say, does anything simplify? Well, yeah, of course, something should. And notice, minus 4bx cosine 2x plus 4bx cosine 2x cancel. 4ax sine 2x minus 4ax sine 2x cancel. And so we actually have something pretty nice. So this is equal to 4a cosine 2x minus 4b sine of 2x. And now we say, hey, look at the coefficients. That tells us that this 4b sine of 2x, really this minus 4b, needs to be 1, and this 4a has to be 0, because that's how we can match the other side. Well, that's not hard to solve. So we come to our conclusion that really, we need a to equal 0. That's what that says. And we need b to be minus 1/4. Okay, now, that gives us what? Well, that says, lo and behold, if we substitute in that our particular solution has to be equal to, and now we put in a is 0, b equals minus 1/4, so minus 1/4 x cosine 2x. Okay, great. All right, now, is there anything else that we need to do? And the answer is yes, there is something we need to do. What we need to do is go back to our problem and make sure we know what we're looking for. Because we didn't say this at the beginning. We just got so excited. What is our answer going to look like? Well, we need the general solution. And so if we're general solution, that says we need the complementary solution and the particular solution together. So we're now ready to write our answer. We basically just add those two together. So our final answer is going to be y, which is our particular solution, plus our complementary solution, minus 1/4 x cosine 2x, plus some constant c, sine of 2x, plus some constant d, cosine 2x. And there we go. That's it. Wow. All right, good. Well, that's a nice one to get us going. You know, get our math blood pumping. Ba-boom, ba-boom, ba-boom. Good, good. All that adrenaline rush, right? All right, number 2. Apply the eigenvalue method to find the general solution of the system. x1 prime equals 6x1 minus 2x2. x2 prime equals 13x1 minus 4x2. Now, you'll see there's this nice phrase, eigenvalue method, which means we're going to be doing something with eigenvalues. And really, that says, hey, we better get some matrices involved here. And so the first thing we should do is let's rewrite this. And so we can take these equations and rewrite this in the form x prime, which has both x1 prime and x2 prime together, is equal to something x. And what goes in here are the coefficients. And just make sure the coefficients are in the right places. So this will be the 6 minus 2, 13, and minus 4. Okay, good. So, first step, let's find our eigenvalues. So the way to find our eigenvalues is we're going to take our characteristic polynomial. So we can do it in a couple ways. So I'll do it in the following ways. We're going to take 0 and set it equal to the determinant of a minus lambda I. You can also do lambda I minus a, but in some sense, if you do a minus lambda I, it's a little bit more consistent in things you might potentially see in other places. And that way you only have to think, okay, it's a minus lambda I is the thing I key off of. All right, so 0 equals a minus lambda I. So that's the determinant, 6 minus lambda minus 2, 13 minus 4 minus lambda. Okay, so 6 minus lambda times minus 4 minus lambda, subtract negative 2 times 13. Okay, so we just have to be patient here. We can multiply the lambdas together. That gives us lambda squared. And then we have minus 6 lambda and plus 4 lambda makes minus 2 lambda. And then minus 24, but over here, plus 26. Okay, so that's plus 2. All right, great, good. Well, now what? Well, we've got to figure out what are the eigenvalues. And, well, if you look at this, you can say, hey, you know, lambda squared minus 2 lambda plus 2, not so clear how to factor that. Because really there's not a lot of options here, right? 2, there's not a lot of things you can do with 2. It's 1 times 2. Okay, great. But what you can do is completing the square. This is lambda squared minus 2 lambda. You say, well, what would I need to add? Well, divide the middle term by 2. It's negative 1. Square it. I'd need to add 1. And then I'd have another 1 because I need to get up to 2. And so, this is really lambda minus 1 squared plus 1. So, what are our eigenvalues? Well, it's about to get a little bit complex. Yeah, you knew that was coming. Come on. All right. So, we have lambda minus 1 squared equals negative 1. Because remember, all this equals 0, which means that lambda minus 1 is plus minus I. So lambda is 1 plus minus I. Okay, so we have our complex eigenvalues. Now, one thing we can always do is whenever we're doing the eigenvalue method, if we want to double check our eigenvalues, and you should anticipate that the eigenvalues should be nice. And, you know, even though they're complex, they're still nice. You can do the following. You can say, okay, what do I get when I add 1 plus I and 1 minus I? I get 2. And lo and behold, if you add up the diagonal, you get 2. It's an easy check. If you multiply 1 plus I times 1 minus I, what do you get? Well, that's a little hard to do in your head sometimes if you're not used to complex numbers, but you get 2. What's the determinant of this? Minus 24 minus minus 26 makes it 2. So those are ways to check. Hey, do I have the right numbers? Yeah, it's nice to check. Okay, so eigenvalues are done. But eigenvalue method doesn't mean just eigenvalues. It really says, hey, you got to check the eigenvectors as well. Okay, so let's do that next. So now the nice thing is if you have complex roots, you only have to find one eigenvector. And the reason that happens is they come in pairs. And we've already seen that there's a pair here, right? 1 plus I, 1 minus I. The fancy word is conjugate, where you flip the sign in front of the I piece. And that also is going to hold for the eigenvectors. So we only need one. So, well, it doesn't matter which one, but let's say, well, let's go with 1 plus I. So let's do lambda equals 1 plus I. Now here's what happens. What do we need? So we're going to look at this matrix A minus lambda I. So this would become 5 minus I, minus 2, 13, and then here it would be minus 5 minus I. All right? Right? Because you take minus 1 minus, well, it's minus 4, then you subtract 1, that's how you get minus 5, and then you're subtracting the I as well. Okay, so that's what we have here. All right, now what happens next? Well, we want to multiply this by some vector. Let's call it AB, and we're going to get out 0, 0. And the goal is, what can we say about AB? Now, you could write this as an augmented matrix. Say, okay, well, this really means 5 minus I minus 2, 13 minus 5 minus I, 0, 0, where this part is really coefficients involving A and B goes there, and what we're trying to equal goes there. But now we're like, oh, this is going to be complicated, except we know the theory. We know the theory says, hey, we can knock out a row. All right, great. Let's knock out that row. Now, could we have knocked out the first row? Absolutely. Knock out any row you like. It just seems like that has smaller numbers, so I'll be biased towards that. And so the punchline is that really what we need to have hold is that 5 minus I times A, so I'm just reading off this equation, minus 2 times B has to equal 0. Or we can say 5 minus I times A needs to equal 2 times B. And now it's our great, hey, there's a really simple way to do this, and it's to do the following. We'll let A be 2, and we'll let B be 5 minus I. And if we do that, the equation holds, and life is good. And so we see that we have an eigenvector that has the following. Namely, our AB, we can pick it to be 2, 5 minus I. Great. So we have an eigenvector, but what we really should do is we should pull it apart into two pieces. So we're going to think of this as 2, 5, and then plus I, 0 minus 1. Okay, so good. We've made great progress here. And now, how do we get our answer? Because whatever is it we're after, maybe we didn't spend a lot of time saying that. We talked about eigenvalue method. Oh, we got to find eigenvalues, got to find eigenvectors. That if you see eigenvalue method, you have to do eigenvalues, eigenvectors. No doubts. But what we need is the general solution. So we've got to translate these eigenvalues, eigenvectors into functions. Now, the way it happens is you would take e to the eigenvalue t, so in this case, 1 plus I t times eigenvector. Now, the problem is we don't like complex solutions. We want to find something real. Keeping it real, that's our goal. But this is where it comes in handy. What we can do is actually combine our answers in some sort of interesting way. Okay, so let me move this up. So this is what you do if you have a a complex root. So we're going to take our e to our eigenvalue, 1 plus I t, times by our eigenvector. Now, justifiably, this is a solution, but it's not the one we want to use. So what we're going to do is say, hey, we know things. This first function can be rewritten as e to the t cosine t plus I e to the t sine t. Now, because they're both ones in there, it's hard to keep track of what came from what. So the 1 in front of the t in the exponent came from the real part. The 1 in front of the t in the sine and cosine came from the imaginary part. Okay, and then we're going to multiply that by what we did here. We split this up into two pieces. 2, 5, I, 0 minus 1. And now we do the following thing. We're going to multiply this out and look at things with no I, so we call it the real part, and things with I, the imaginary part. And that makes it 2 pieces, and the moral is each piece is a solution. And therefore, that gives us our 2 solutions that we're looking for. Okay, so first off, how do we get the real parts? Well, e to the t cosine t, 2, 5, and then I, e to the t sine t, and I, 0 minus 1. Those will give us real parts because I squared is minus 1. So this will give us e to the t cosine t, 2, 5. Okay, I squared is minus 1. So minus e to the t sine t, 0 minus 1. Okay, so that is one of our solutions. Now the other solution is going to come from the imaginary parts. And the way we get our imaginary parts, well, you'll multiply e to the t cosine t by the I 0 minus 1, so the outer parts, and the e to the t sine t by the 2, 5. Okay, so if we do that, what will we have? Well, we'll have, so the e to the t cosine t times 0 minus 1, right, the outside parts, and then the inside parts, and e to the t sine t, 2, 5. All right, so the real part and the imaginary part of this function. This is a solution, and this is a solution. And if we want the general solution, the way we do it is we get combinations. And therefore, the general solution looks like some constant c times that function plus some constant d times that one. And that's the answer. Done. So this one is a little bit more interesting because we ended up getting complex roots. Complex roots can be a little bit more subtle to work with if you're not comfortable with it. Now, what will be on the exam? We may not even have a problem like this on the exam, but just be ready to deal with, there are sort of kind of 3 situations you might encounter. Namely, we have distinct roots and distinct real roots. Okay, that's pretty nice. And we find the roots, find the different eigenvalues, and for each eigenvalue we find the eigenvector and put them together, where life is good. We have complex roots, which is what we did here. In that case, things come in conjugate pairs. And that's how we're able to extract our functions here. So know how to get that. And the third thing that we might encounter is when we're sort of missing an eigenvector. And who knows, we haven't finished this practice exam. That might show up on one of these problems later on. But those are the 3 things you want to be able to do. And so there we go. All right. Well, that was fun. Let's keep going. Number 3. So consider the linear ODE system. So we have x prime, -1 3/2, minus a 6, minus 2x. And then it says, part A, verify that minus 3, 1, and oh, that's really small text there. I have to really get my glasses to there. E to the minus 3t over 2, and minus 3t minus 6t, e to the minus 3t over 2, are both solutions to the ODE system. Now, one way we could go about it is we could actually solve it and somehow show that these work. That's not what you want to do. If someone says verify something, you say, look, I'm not starting from scratch. I'm going to just use what they give me. And so let's do that here. Okay, so let's, we have 2 functions. We got to verify both. So let's start with our, we'll start at the first one, right? Seems logical. If we're going to have to do both, there's no reason to pick one over the other. Okay, so minus 3, 1, e minus 3t over 2. Okay, so what we need to do is plug it into both sides of the equation and see what happens. So we'll look at x prime. Well, there's no t there, so that's pretty straightforward. So it's just e to the minus 3t over 2. And derivative of this, well, minus 3 over 2 comes down. So we can say, all right, this is the same as minus 3, 1 times minus 3 over 2 e to the minus 3t over 2. Well, if you want, we can put the 3 over 2 on the inside. It's minus 9 over 2, 3 over 2. Whoops. I forgot there's a negative here. So there's a negative, which makes this a plus, makes that a minus. Okay, keep track of your signs. Negative signs are oftentimes one of the hardest things to keep track of, and a place where a lot of people lose it. Okay, so that's our x prime. We haven't verified anything yet. Now we've got to do the other side. Okay, so the other side, minus 1, 3 halves, minus 1/6, minus 2, x. All right, so minus 1, 3 halves, minus 1/6, minus 2 times this part, minus 3, 1, e to the minus 3t over 2. Okay, so we're going to get 3, right? So work it through there. 3 plus 3 halves. Well, 3 is 6 over 2. Then plus 3 over 2 makes it 9 over 2. Then we get negative 1/6 times minus 3 is 1/2. Subtract 2, which is negative 3 over 2. And that's e to the minus 3t over 2. And now we've plugged it into both sides, and here is the check. We say, aha, these match, and so it is a solution. All right, so that's how you do it, right? Plug it into both sides and see, hey, does the same answer come out? And if we do get the same answer, life is good. If we don't, then we're in trouble. Now the next one, because we got to verify both, right? So we got to do this other part. This is going to be slightly more interesting. And I'm going to recommend we do something, because notice how the vector also depends on t. So previously, the vector didn't. We could treat it like a number. Like, oh, okay, great. Well, if we treat it like a number, nothing to worry about. It's like, we know what we're used to. It's like a constant. But now, that varies. So what I'm going to recommend we do is we move that e to the minus 3t over 2 inside. And so I'm going to think of it in this way. So this is going to be minus 3t minus 6, e to the minus 3t over 2, and t, e to the minus 3t over 2. So this is one way to write it, and I believe that this will be the most convenient for when we're doing the x prime. So here we go. What is x prime? Well, all right, got to do the derivative of the top. Okay, product rule. So minus 3 e to the minus 3t over 2. And then we're going to have minus 3 over 2 times minus 3t minus 6 e to the minus 3t over 2. And then down here, product rule, e to the minus 3t over 2 minus 3 over 2 t e to the minus 3t over 2. Okay, now if we wanted to, and for some reason I feel the want, we could do a couple things. Now I can pull the e to the minus 3t over 2 out. All right, so I'll do that. Downstairs, well, no big surprises. We get 1 minus 3 halves t. Upstairs, we'll have a minus 3. Then we have minus 3 halves times minus 6. Well, what does that do? Minus 3 halves times minus 6 is going to be a plus 9. So plus 9 minus 3, that combines to give us 6. And then we have plus 9/2 t. All right, good. Now, on to the other part. Okay, so we're going to need a little bit of space for this. So we're going to take our, again, -1 3/2 -1/6 and -2 times x, which is -1 3/2 -1/6 -2 times, and here I'll leave the e to the -3t on the outside. Now you're probably wondering, how do I know whether to leave it in or to leave it out? And the answer is, it won't matter. It's just slight bookkeeping. And it's just I feel more comfortable thinking about product rule in this format where we think product rule of each piece than product rule in that format. All right, e to the -3t over 2. Okay, so this will be, well, -1 times -3t over 6. Well, that's 3t plus 6, right? 3t plus 6, and then plus our 3/2 t. All right, boom, boom. Then down here, times it by minus a 6. Okay, so 3 times a 6 is half. So we're going to have a 1/2 t. And minus 1/6 times -6 is plus 1. And then we're going to get -2t. And this is still multiplied by e to the -3t over 2. And now, well, 3t plus 3/2 t, that's really 6/2 t plus 3/2 t, which makes 9/2 t. And then there's a 6, so we have 6 plus 9/2 t. Downstairs there's a 1. We have a 1/2 t, and subtract 2t. So that's subtracting 4/2 t. A half minus 4/2 is -3/2. And that's e to the -3t over 2. And now we say, okay, what happens? And we stare at these, and we don't have to stare very much. We see, aha, they match. All right, so there's a lot of bookkeeping that had to go on, but the thing is, it's a very mechanical process. So don't be intimidated by the bookkeeping. It's simply a matter of take an expression, plug it into both sides, and compare the answers. Take an expression, plug it into both sides, compare the answers. And in this case, well, things got a little bit hairy at some points, but the process was never so bad. Okay, now that's part A. Part B. Find a solution to the ODE system with x of 0 equals 0, 2. Well, the thing is that we have these pieces. They're both solutions. So we say, all right, we believe that they should be linearly independent. Now, we haven't proven it. We're not going to, because it doesn't ask us to prove it. But we're going to go on faith, and so what does that mean? Well, that means that we're going to say, okay, we are going to say that our general solutions look like some constant, c, times -3, 1, e to the -3t over 2, and plus some constant d, -3t minus 6, t, e to the -3t over 2. And now what we do is we plug in 0. So x of 0, which should be 0, 2. So we say 0, 2, needs to be somehow coming out here. So when you plug in 0, the e to the 0 goes away. Also, the pieces with t go away. So what we get is some constant c, -3, 1, plus some constant d, and -6, 0. Okay, now the nice thing, these are two equations, two unknowns, and they're relatively straightforward to solve. Because, notice, the first equation says -3, c minus 6d equals 0, right? Just minus 3c minus 6d equals 0. And then the second equation says c equals 2. Right, c plus 0d equals 2. Well, now, great. C equals 2. That means c equals 2. No surprises. And here we say what? Well, plug in c equals 2. You get minus 6 equals minus 6d, or you could say 6d equals minus 6, d equals negative 1. And, you can go back and check. If c equals 2 and d equals negative 1, you get minus 6 plus 6, which goes away, 2 plus 0, which is 2. And so we say, aha, now the last thing for us to do is to write our answer, because we know c and d, so we replace c and d by the appropriate values. And so we'll say that our solution is 2 minus 3, 1, e to the minus 3t over 2, and minus 3t minus 6, t e to the minus 3t over 2. Now, if we wanted to, we could smoosh this all together into one single vector, if we wanted to. And you can tell by my voice, we probably don't want to. I don't think there's any advantage to doing that. And so we'll just leave it as our pieces put together. Great. All right. Good. Ha-ha. We're halfway there. Halfway there. All right. So let's go to number 4. So use the matrix exponential e to the at to solve the system of ODEs. X prime equals ax. A is this matrix. Minus 5, 1, 4, minus 2, with an initial value, x of 0 equals 3, 2. And it says, hey, here's a reminder, x of t equals e to the at, x of 0. And you're probably thinking, it would be nicer if you said, oh, here's how you compute e to the at. Well, let's just run through it. Okay, so here we go. It's going to be fun. And so the easiest way to compute e to the at, well, I shouldn't say the easiest way. There's a couple things that happen. But let's kind of remember where e to the at comes from. And so one of the places it came from was when we talked about the fundamental matrix. So we could say, e to the at is this phi of t times phi 0 inverse. So where phi of t came from our solutions to x prime equals ax. So every solution became a column. So for 2 by 2, probably the easiest thing to do for us to compute e to the at is to find the solutions. Now there's some exceptional things. For example, if all the eigenvalues are 0, then it's just super easy to go straight to the definition to compute e to the at. But that's not the case here. All right, so we're going to run through it. So for a lot of the first part of this problem, it's going to feel like, isn't this eigenvalue method? It is. It is eigenvalue method where what we're doing is we're using the eigenvalues to compute the solutions, because the solutions are going to fill up this phi of t. So let's get going. We'll have some work ahead of us. So 0, set that equal to the determinant of a minus lambda I. And okay, so that's the determinant of minus 5 minus lambda, 1, 4, minus 2 minus lambda. So that's minus 5 minus lambda, minus 2 minus lambda, and subtract 1 times 4. All right, so we get lambda squared. And then we have minus 5 times minus lambda. So, see, well, let's just make life easy. Notice how everything has a negative? That says we could factor 2 negatives out, and we could just turn all these to positives, and then we'll be okay. All right. So that just makes it easier for us to talk about what's happening. So we have 5 lambda and 2 lambda, which makes a 7 lambda. And then we have 5 times 2, which is 10. 10 subtract 4 makes 10 subtract 4 makes 6. So that would be lambda plus 1, lambda plus 6. Ah, nice. Distinct eigenvalues. And we're keeping it real. Yeah, woohoo, keeping it real. All right. So our eigenvalues are -1 and -6. All right, good. And like we talked about before, if you add those up, that should be the same as adding up what's on the diagonal, which is -7 is -7. If you multiply these, we get 6, which is the determinant, which is 6. Good. You know, it's nice to sort of pause and say, okay, did I do this right? Did I do this right? You know, because on a test, one small mistake at the start will sink you later on. And okay, so we've got our start here. So next up is we've got to tackle finding our eigenvectors. Okay, so let's do lambda equals -1. That says, what do we need? Well, what we need, -5 minus -1 is really -4, 1. And here it was 4 minus 1 times some vector AB equals 0, 0. Well, you can see these are really the same equations, upstairs and downstairs. The only difference is the sign. So -4a plus b equals 0. And so what we see, if we think of our eigenvectors AB, well, b equals 4a. And so that has the form of a 4a or a 1, 4. So here is our eigenvector. So for this eigenvalue, that's our eigenvector. Now we can check this. So we can multiply this matrix A by the vector 1, 4. So if you did that, what would you have? So you'd have -5 plus 4, -1, that's good, because we want to end up with -1 times 1. Then you have 4 minus 8, which is -4, which is again -1 times 4. So, yep. So you can check if an eigenvector is an eigenvector, just multiply it by the original matrix and see, does it scale? If it scales, you did it right. And if it doesn't, do it again. You know, it's always good to sort of slow down and say, hey, you know what? I'd rather make sure I take my time and get everything right than to speed through it, make a mistake, and just sink myself later on. Now that we've had a little bit of practice with that, we'll repeat lambda equals -6. Okay, so we're going to put -6 in here, and we'll get 1, 1, 4, 4, and we're looking for something AB to get 0, 0. Well, again, you can see it's essentially the same equation, right? This says A plus B equals 0, and this one says 4A plus 4B equals 0. So I say, all right, look, if A plus B equals 0, well, that's really the same thing as saying B equals -A. So our vector looks like AB, which is A minus A, which is A 1 minus 1. And like, oh, okay, well, that was pretty clean. And again, you can check. You get -5 minus 1, which is -6, which is good. Then you get 4 plus 2, which is +6, which is good. So I multiplied A by that vector and said, hey, it does scale. That means my eigenvector is actually an eigenvector, which is what we'd like to be true, right? Of course, of course. Okay, so we're enjoying ourselves. We're having a fun time. But now, say, what have we really done here? What we've done is we've actually found 2 solutions. And in particular, what we can say is we say, okay, we have the solutions are e to the eigenvalue t, so e to the minus t 1, 4, which we write as e to the minus t 4 e to the minus t, and here, e to the minus 6t, so e to the eigenvalue t, times the vector 1 minus 1, which we'll write e to the minus 6t minus e to the minus 6t. Okay. Now, the next step for us is we have to, because remember, our goal is we need to use e to the at. We have to use e to the at if we want to get all the points. And remember, we're going to channel our inner Pokemon. Got to get them all. Got to get all the points. And so we're going to follow the directions precisely so that we're like, aha, we're getting the points. Okay, so what we're going to do now is say these solutions, coming back here, are the columns of 5t. Or you could say that they're the columns of phi of t. Well, that's really the same thing, phi or phi, whichever one you want to use. And so we're so close now. And what we can say here is that phi of t is e to the minus t, and 4 e to the minus t, and e to the minus 6t, and minus e to the minus 6t. All right, but we're not yet to e to the at. To get to e to the at, we need to multiply by phi 0 inverse. All right, so let's start by saying, what is phi of 0? It's going to sound really familiar. If you plug in 0 into here, you'll get 1, 4, 1, minus 1. You're like, whoa, hey, that looks an awful lot like my eigenvectors. Yeah, it will. It will. Okay, so what's phi 0 inverse? Well, there's two ways to do it. You can go through the process or recall the formula. And you might say, wait, there was a formula for this? I'll tell you both. So let's do the process first, and then we'll do formula. So the process, which is how I often like to do these, is you start by writing the matrix you're taking the inverse of, and then you have next to it the identity matrix, 1, 0, 0, 1. And the goal is to make this look like the identity matrix using our operations. So we have three of them. You can swap rows, multiply a row by a non-zero, and then there's a weird one where we can combine a multiple of one row, add it to another row. And the third one is the most powerful. Okay, so there's lots of ways to proceed. I like to work column by column. And so, for instance, I say, well, that first one is good. I like that first one. I want to knock out that 4. So multiply by -4 and add down. And if we do that, we haven't changed the first row, but now we'll have 0, -4 plus -1 makes -5, and -4 and 1. Now multiply this row by -1/5. Okay, and if we do that, we'll make this a 1. Because the first column is good to go. Now clean up the second column. So that'll give us a 1, 1, 1, 0. Haven't changed the first row. 0, 1, 4/5, -1/5. And now I just want to knock that 1 to a 0. So use the bottom row going up. And what will we get? Well, we'll get 1, 0, 0, 1, which is great. The bottom row hasn't changed, which is great. And then multiply by -1 and add. So -4/5 plus 1 makes +1/5. And then -1/5 times -1 makes a +1/5. And there we go. There we go. So this part over here, this is our phi 0 inverse. Okay, so phi 0 inverse, everything has a factor of 1/5 in it, so we could pull out a 1/5, and we can get, this is 1, 1, 1, 4, minus 1. Okay, now at this point you're probably thinking, whoa, deja vu. Isn't that what we started with? Well, yeah, sometimes it happens. You can, now, if you're like, hey, this doesn't seem right, what can you do? And the answer is you can multiply the matrices together, right? So 1 plus 4 is 5, times a fifth is 1. 1 minus 1, 0. Then you have 4 minus 4, 0. And then the last piece would be 4 plus 1 is 5, times a fifth is 1. So you can always check and see whether or not you get the identity at the end when you multiply the two together, and that's the way of checking your answer. Now, so that's the first way. We're going to come back and use this in a second to answer our problem. But before we do, I promised there was a second way. So here's the second way. So there's a formula. So here you go. If you have a 2 by 2 matrix, A, B, C, D, and you want to take the inverse of it, it's 1 over A times D minus B times C. And if you're like, that sounds like the determinant, it's because it is. So hey, good for you for recognizing that. And then what you do is you swap where A and D are. So D, A. And then you flip the signs for B and C, minus B and minus C. And then that's it. That's the determinant. So if you memorize the formula, that works great. If you remember the process, that works great. Now you might say, well, wait, does that actually work? Well, let's try it here. So if we're after 1, 1 for minus 1 inverse, what would that tell us to do? Well, we take 1 over the determinant, so it's minus 1 minus 4. So it's minus 1/5. And now swap the entries on the diagonal. So that would make this a minus 1 and a 1. And then negate the entries in the corners, minus 1 and minus 4. Well, of course, you can put the minus back in. So that would be 1/5. And you'd get 1, 1, 4, minus 1. All right. Now you're probably thinking, that seems so much easier. Why don't we just always do that? We could. But one of the things I often worry about is trying to remember too many formulas, because there's only so much space in here. You got to be like, okay, I need this formula, I need that formula, I need this idea, that idea. And so for me, I personally, and you're seeing my own biases coming out, I personally strongly prefer to memorize sort of the processes. And if I understand general processes, then I can apply that to handle lots of cases simultaneously. And I feel that's a much better use of storage here. Okay, now, are we done? No! But we're out of paper space. Okay, so that's okay. Paper grows on trees. So we have more paper. So we're going to keep going. All right, so let's move this up. And where are we at? So we have phi 0 inverse. So our next step is we're going to do our computation. So e to the a times t is phi of t, and phi 0 inverse, and I'm just going to copy down these pieces here. E to the minus t, 4 e to the minus t, e to the minus 6t, minus e to the minus 6t, and 1/5, 1, 1, 4, minus 1. Now, I could multiply these out, but justifiably, this is e to the at. So I'm going to leave it like this. Okay, now we run back to where we started, which says use the matrix exponential e to the at to solve the system. Remember, x of t equals e to the at times x of 0. Well, we have e to the at, and we have x of 0. We put them together. So our solution, x, will be e to the at, x of 0. So that is e to the minus t, 4e to the minus t, e to the minus 6t, minus e to the minus 6t. Then there's a factor of 1/5, 1, 1, 4, minus 1, and then 3, 2. Okay, so I'm going to work my way over. So let's start by doing this multiplication on the end. So what will that be? Let me just move this up here. So we're going to have 3 plus 2, 5, times, okay, so I'll just put a 1/5, 5, 3 plus 2, 5. 12 minus 2, 10. And then times the rest of this. And we just copy that down. All right, go ahead and multiply the 1/5 through. And so we'll have lots of copying here. We probably could have done the 1/5 at the previous stage, but we'll have 1, 2. And now, that's a super easy multiplication to carry out. And what do we have? We have e to the minus t plus 2e to the minus 6t. And then we're going to get 4e to the minus t, and then minus 2e to the 6t. And we're done. Because we found e to the at, and we used it to solve the initial value problem for our differential equation. Now, you might pause and say, that did not seem the most efficient way to solve this problem. It may not have been. But in some sense, we're testing on this problem. Do you understand what e to the at is? And do you understand how to use it? And so it is absolutely true. It was not a very efficient way to solve it. But it was a good chance for us to say, hey, we understand principles. In particular, we know how to get e to the at is this product of phi of t, phi of 0 inverse. So this was really the key here of understanding that. All right, well, that was a good one. And let's go on to the next one. Number 5. Ah, sweet! We've done it! We've reached the place where we have Laplace transforms. Woohoo! We knew this was coming, and now we're here. Yes, yes, yes. Okay, so find the inverse Laplace transform of this expression. Okay, so the way we're going to do it is, of course, we have our table here we're going to use. But we recognize that in order for us to use our table, we have to do something. We need to pull this apart. So our future is going to have a lot of partial fractions in it. So here we go. Here we go. Now, the way we pull it apart is we're going to do the following. We say, look, this is 20s upstairs. Downstairs, this is s squared plus 4. And we can pause for a second here and say, is that s squared minus 4s plus 20? Is that really factored as far as it can go? Maybe we should just double check. It feels like it is. And if you look at this, this is the same as, think about completing the squared. S squared minus 4s, what would you need to add to that to complete the square? Well, negative 4 over 2 is negative 2 squared is 4. Then, of course, add 16 more, which makes s minus 2 squared plus 4 squared. So that means the complex roots. It also means that's factored as far as it can go. Okay, so great. We have two irreducible quadratics downstairs. Irreducible quadratic is also another fun way of saying complex roots. So that means that the first thing, which is finding the form of our partial fraction, is we're going to have two pieces. And the first piece, okay, that's the s squared plus 4 downstairs. And the second piece is the s squared minus 4s plus 20 downstairs. All right, upstairs, well, because these are irreducible quadratics, we actually have to have what we would call linear terms, as plus b and cs plus d. Whoops, that should be a plus sign there. All right, so now we have to solve for a, b, c, d. Yes, we do. Well, let's start thinking about how we can go about doing that. And, well, we do it the way that we always do, which is first start by, once we have our form, clear out the numbers. By the way, quick check. How many constants do we have to solve for? 1, 2, 3, 4. All right, what's the degree of the polynomial down here? 4. Okay, that's a good check that we haven't, at least there's a good chance that we got the right form. Okay, clear out our denominators. And what will we have? Well, we'll have 20 times s equals a times s plus b times s squared plus 4 and plus c times s plus d. Whoops. Not that. We'll get a, okay, we'll cross out all that. 20s, as plus b. It's the s squared plus 4 cancels. So we will have s squared minus 4s plus 20. And here, cs plus d times s squared plus 4. Okay. Now, you might say, okay, let's choose wisely. There's not really a good choice here. There's no choice that you can make which cancels everything but one value. And so choosing wisely is not going to help us very much. Now we can choose things like, okay, choose 0, and then you can get some nice relationships between, say, b and d, but that's not going to be the best way to approach it. So what can we do? Well, if you can't choose wisely, go to coefficients, which means that we're going to expand. We're going to expand it out. FOIL. Wow. Okay, so multiply this out. as times s squared. And when we talk about FOIL, really we just said take every possible choice here, multiply by every choice there. So there's going to be like 6 terms here, because there's 2 choices times 3 choices, and 4 terms there. So there's going to be a lot of pieces here. So we'll get as cubed minus 4as squared plus 20as. Okay, that's multiplying the as by everything. Then we're going to get bs squared. I'll just write that underneath here. bs squared minus 4 times b times s and plus 20b. Then over here we'll get cs cubed. And then we'll get 4 times c times s. And then we'll get d times s squared. And then we'll get 4 times d. Okay, so that leads us to the following. Namely, we get a plus c s cubed, and then, a lot of stuff here, plus minus 4a plus b plus d s squared, and then plus 20a minus 4b plus 4c times s, and 20b plus 4d. Okay, so we multiplied it out, we gathered our coefficients, and now we say, hey, this has to match with that. So a plus c has to equal 0. Minus 4a plus b plus d has to equal 0. 20a minus 4b plus 4c, well, that's got to equal 20. And 20b plus 4d has to equal 0 because there's no constant term. So now we have 4 equations with 4 unknowns. Oh boy, oh boy. And, well, we just start thinking our way through it, you know, a little bit at a time. And we can set up an augmented matrix and we can solve, or we can sort of chip away a little piece here and a little piece there. And let's see, is there any easy candidates? Things that we can look at and say, aha, here are some things that we can make progress on. At this point, I'm just going to pause and say, if you're looking at the clock, you're like, we're almost to the 75-minute mark, Steve. And we've got a lot of time left on this problem, and this is not the last problem. Am I going to be able to finish the test? So I want to assure you, if you're watching this right now, yes, these problems are going to push you, on the practice. The practice problems are hard. They're actually a lot harder than what you should expect on the test. So don't be panicking, okay? And you might hear my voice like, oh, we got to solve these. But, I mean, it's not like we're looking at this and saying, these are unsolvable. It's just sort of like, well, it's going to take us some time. That's okay. We'll be okay. You'll be okay. All right. So here we go. Let's do augmented matrix style. So how does that work? So we're just going to set up our equations. Again, a plus c equals 0 minus 4a plus b plus d equals 0. So I'm just copying what you see here. And then 20a and minus 4b plus 4c equals 0. And 20b, plus 4d, not, this part doesn't equal 0, this equals 20 equals 0. All right, so if we think about this as an augmented matrix, the augmented matrix is really saying, here's this system of equations. We're just going to use a matrix to help us shorten our notation here. So we're going to have 1, 0, 1, 0, minus 4, 1, 0, 1, 20, minus 4, 4, 0, and 0, 20, 0, 4, 0, 0, 20, 0. And what we would want to hope for is, well, if we can reduce it all the way down to the identity, that's good. It's actually just enough to say, can we get something simple enough that we can work with? So let's do a couple of things. We can add multiple 4 down, and here we can add a multiple of negative 20 down. And if we do that, what will we get? Well, first row will be the same. And then we'll have 4 plus negative 4 makes 0, 1, 4, 1, 0. Negative 20 plus 20 makes 0, negative 4. And then minus 20 plus 4 is minus 16, and 0. And here is 20. And then we have our 0, 20, 0, 4, 0. Okay, good. Now, well, let's clean up a little bit. everything here is a multiple of 4. So suppose we multiply this row by negative 1/4. Clean it up. Okay, so if we do that, well, the numbers will become smaller. We like that. Usually small numbers mean simpler to work with. Usually. So we have 0, negative 4 times negative 1/4 would be 1. And then we have 4 and 0 and 0, 0, negative 5 and 0. And, well, while we're at it, let's multiply this row by 1/4 as well. And so 0, 5, 0, 1, 0. And now, I think you see what I see, which is, hey, look at these two middle rows. They're really close. 0, 1, 4, 1, 0, 0, 1, 4, 0, negative 5. This slot right there is the only difference. So what you can do is you can multiply here, negative 1, and add up, because you can knock out a couple of entries simultaneously. And now, if you do that, what do we have? Well, first row, we're not changing anything. Second row will be 0, 0, 0, 1, 5. Then 0, 1, 4, 0, minus 5. And 0, 5, 0, 1, 0. Okay. But now we're ready. Let's watch what happens. We're going to go through this and see, aha, this equation, let's start with that. That tells us what? If we read off what it says, 0a plus 0b plus 0c plus d equals 5. So we get that d equals 5. Okay. Well, I didn't do a good job with my arrow there. Okay, so that's the first row we look at. Now we say, hey, we know D. Is there any place where if we know D, we're in good shape? And now we're like, well, hey, check out this next piece. See, it only involves B and D. And so if you read it, it says 0, 5b plus d equals 0. 0a, 5b, 0c, d equals 0. But we know that d equals 5. So this says that 5b is negative 5, which says b is negative 1. So we say, aha, that was our next piece to use. And now we're like, hey, look at us. Now we know B and we know D. Where are we going to go next? Well, I'd recommend this row here involves B and C. Well, B we know, and so that means if we use that information about B, now we can gain information about C. Okay, so reading off that row, 0a plus b plus 4c equals negative 5. Well, but again, we know b equals negative 1. So that says minus 1 plus 4c equals negative 5. Well, what does that say c needs to be for this to work? So that says, hey, c has to be negative 1. And now we're like, wow, we're doing great. We now know B, we know C, we know D. What don't we know? We don't know A, but we haven't used the first equation yet. Okay, so our first equation, this one up here, says what? Well, it tells us that A plus c has to equal 0, but we know what c is. A minus 1 equals 0. So that says, oh, a has to equal 1. All right, we did it. We've done it. Oh, yes. All right. So what have we done? Well, what we've done is we've now solved for a, b, c, and d. Now, if you're unsure about the process, what just happened? Well, what we did is we just set up our system of equations, and we just sort of chipped away and said, well, try to knock things out a little bit at a time. Now, we could have kept going and doing more with this augmented matrix until we were satisfied that we'd knocked everything out. But once you have enough to sort of like prime the pump, you know, get like the first term going, then you can oftentimes get this domino effect. It's like, okay, I have the first value, which gives me my next value, which gives me the next value, which gives me the next value. And so oftentimes we just need to start. What if you're paranoid? You're like, oh dear, did I make a mistake? What can you do? Well, if you have these answers, you can go back and check. Okay, a plus c. 1 plus minus 1. Yeah, that equals 0. Minus 4a plus b plus d. Okay, so minus 4a, so that would be minus 4. Plus b would be minus 1. Plus d would be plus 5. So minus 4 minus 1 plus 5. Yeah, equals 0. Nice, good. So 20a would be 20. Minus 4b would be plus 4. Plus 4c would be minus 4. That equals 20. And then 20 times b would be minus 20. 4 times d would be positive 20. And that gets us to 0 again. So everything checks out. We're good to go. Good to go. Okay, so let's pause for a second and say we could have done something slightly different on this problem if we had a different technique. And this is something I don't normally like, but I do want to point out that there is an option that we can go by that is available. And so I want to tell you what it is and explain how it works. And it might shave a little bit of time off our problem. This is not to say this is what you should be doing, because on a test, you often go with something which you're comfortable with. And if you're not comfortable with what happens in the next few minutes, that's okay. And again, on a test, this is an unreasonable problem for a test. But, you know, why should that prevent us from talking about it? Okay, so I rewrote down our set of equations. And again, our goal is to solve for a, b, c, d. Now, what do we normally do? We say, well, make good choices. And we say, okay, well, why don't we choose things which zero stuff out? All right, so what can we do here? Well, what we can do here, let's start with this part. So what would make s squared plus 4 equal to 0? All right, so if I want the s squared plus 4 to be equal to 0, well, that says, okay, you can choose either s equals plus or minus 2i. So now let's plug in 2i and let's see what happens. So we're going to plug in 2i. And what do we get? Well, the last term will go away. All right, because that's why we chose it. The left-hand side will become 40 times I. And this will be equal to, plug in 2i, so that would be 2ai plus b. Then here, 2i squared is minus 4 plus 20 makes 16. Then minus 8i. Now expand out. And what do we have? Well, we'd have 32ai, and then minus 16ai squared, then plus 16b, and minus 8bi. Well, the I squared is the same as minus 1, and so these two parts don't have any I attached, and then these two do. So we're going to group. So this would become 32a minus 8b times I, and then plus, because minus 1 minus makes 16a plus 16b. And now we're going to pull out a little fact. And the little fact that we don't really allude to very much, but will be nice for us to know, and we'll put it over here in this corner. Fact, our coefficients, and in this case, that means A, B, C, D, will be real. In other words, they're real numbers. But notice I have I attached here. Well, that says what? Well, that says if you're looking at complex numbers, you look at real part and you look at imaginary part, and they have to match. So the imaginary part here, 40, has to match here. So this has to equal 40. And then the real part, well, there is no real part. So that says this part has to equal 0. And now we say, oh, wait. If 16a plus 16b equals 0, that tells us that a equals negative b. All right. Well, now, what does that do? Well, one thing we can do is, okay, that says minus 8b is the same as plus 8a. So now, that would tell us that 40a has to equal 40, or a equals 1, which says that b equals minus 1. And now we have our coefficients for a and b. Now we go to the other part. See how quickly that can be? If you know the fact and you're comfortable using complex numbers. If you don't know the fact, or you're not comfortable using complex numbers, what we're doing right now is going to feel not very good. Okay, so now we do the other part. Okay, so now we come to the s squared minus 4s plus 20. So we want to make this part equal to 0 so we can solve for the other terms. All right, so what can we do? I would pause, by the way, and say, once you know a and b, you can plug in a and b, and then if you set s equals 0, you get d, and then it's almost a freebie to get the last one. But let's go ahead and finish the process. So if we want to have s squared minus 4s plus 20 equals 0, well, remember, this was the same as s minus 2 squared plus 4 squared. And so we get that s would be 2 plus or minus 4i. So let's plug in. It doesn't matter which one we plug in, either 2 plus 4i, 2 minus 4i. You just pick one. So now we're going to plug in s equals, well, let's do the plus. I'm an optimist. I would rather do the plus. S equals 2 plus 4i. So we're going to plug it into both sides. Now, the part here is gone. Nothing needs to be done. So what do we have? Well, we have 20 times 2 plus 4i. We'll clean that up in a few minutes. This is going to equal, and over here, we're going to get c times 2 plus 4i plus d times 2 plus 4i squared plus 4. All right, this is going to be a more interesting computation. Or we'll get 40 plus 80i equals, and now we'll expand here. We'll get 2c plus d, so 2c plus d, and then plus 4c times I. And then here, well, what will happen? You're going to get 2 squared, which is 4. You get 4i squared minus 16, and a plus 4. So if you multiply all of that out, right? Again, what's happening? 2 squared is 4, 4i squared minus 16, and plus 4, all combined gives you minus 8. And then you'll have 8i twice, so plus 16i. All right. Whew. Wow. Okay. There's a lot to do here. Now we can work on cleaning this up. Now, one thing we can do before we get too far along is say, well, hey, this has factors of 8 out of here. So let's take both sides and we're going to multiply it by 1/8. So that would just make things a little bit cleaner. So we'd have 5 plus 16i equals 2c plus d plus 4c times I, because we're going to pull the 8 out of the second piece, minus 1 plus 2i. All right, that's definitely going to be a little bit easier to work with. Okay, time for us to do our expansion here. So we're going to have minus 2c plus d, and then here we'll get plus, all right, as 4c plus 2di, so that's our outer terms. And then here we have minus 4c times I. Okay, there's that term. And then we're going to have 4c times I plus 2i. That'll be plus 8ci squared. But we now group. And, well, whoops. 80 times an eighth, that's 10, not 16. Sorry. Sometimes you gotta double check your work. All right. What do we have? Well, we have the real part is minus 2c minus d minus 8c, because that is I squared is minus 1. So minus 10c minus d. And the imaginary part, 4c plus 2d subtract 4c, so plus 2di. And now we do our matching game. So matching, we'd say, hey, the 10i matches to 2d times I, so that's great. That says that 2 times d equals 10, or d equals 5. And then the 5 is going to match with the minus 10c minus d. But what do we know? We know what d is. D is 5. So, lo and behold, we can now say that minus 10c minus 5 equals 5, or minus 10c equals minus 10, or c equals minus 1. And now we have our A, B, C, D. And the problem then proceeds as we did before. All right, great. Now, was this easier? Maybe. But it's at least an alternative. So if you don't like having to solve 4 equations and 4 unknowns, it boils it down to saying, oh, well, you really have a pair of 2 equations and 2 unknowns. So, there's options. All right, back to our regularly scheduled problems. All right, now, are we done? No, we're not. And again, we've run out of page, but that's okay. Paper grows on trees. We're going to use a lot of paper on this practice. Okay, so let's talk about what we have done. So, remember up here, we had this part. So, here we go. Let me grab this pen. We said 20s divide by s squared plus 4 times s squared minus 4s plus 20 has the form as plus b over s squared plus 4 plus cs plus d over s squared minus 4s plus 20. And later on, at the bottom here, we figured out our choices for A, B, C, D. So this is equal to S minus 1 over S squared plus 4. And then C would be minus S plus 5 over S squared minus 4S plus 20. Okay, so, all right, let me start to there. So, now, one other thing we didn't write down, but we'll just make a quick note here. This we said was S minus 2 quantity squared plus 4 squared. Now we need to sort of start thinking about what do these look like. So we're ready to start glancing at our table. And the thing that should jump out to us are sines and cosines. So sine of AT looks like A over S squared plus A squared. And cosine of AT looks like S over S squared plus A squared. So, for instance, we can write this as the first term because we have the S squared plus A squared and downstairs. So we could say, okay, so I'm going to put a little squiggly line. This is equal to S over S squared plus A squared. And I'll go ahead and write it as 2 squared. And now we're happy with that. And then the next part, well, we have the minus 1. Now notice if we're going to do sine, we would really want to have an A upstairs. It's A over S squared plus A squared. And our A squared is 2, so we'd really, really like there to be a 2 upstairs. So we're going to put it. So we're going to put a 2. But we should have minus 1. So minus a half. All right. Great. Now, the next part will be the fun part. So I'm going to tackle the this part here. And what to do? The next part is not magic, and I don't want it to appear like that, but you'll notice we don't have, actually we do have it right here, e to the at kt and e to the at cosine kt. You notice how we have, when there's an s minus a plus k squared, the top involves an s minus a, and then this part involves a k. So, looking at that, I say, all right, because there's an s minus 2, what do you want to do with this minus s plus 5? Well, what we'd like it to do is have this s look like that. So I'm going to think of the top as minus s minus 2, because that'll give us the s minus 2 to match. But I'm not done writing the top yet. We have the minus s, it's minus s plus 2, plus 3 more. So, plus 3. Okay, so now going back to this part, so we have, let's do the s minus 2 part first. So minus s minus 2 over s minus 2 squared plus 4 squared. And then our last part is the constant part. Okay, and it's being added. And s minus 2 squared plus 4 squared. We want this would match, we should have, if it's k squared, it should be k. So we should have a 4 up there. What does this say we should have? It says we should have a 3. But we want a 4. So we're going to put a 4. So how do we compensate? Well, multiply 3/4 in front. So the punchline here is that all of our work so far has been to say that this part is equal to f of s. We did our partial fraction decomposition, and then we broke it up. So now we're ready to do the inverse Laplace transform here. And say, okay, so what happens to each piece? And we actually know. This part will go to cosine of 2t. Okay, so I'm not going to pull it up for every term, but see, that's cosine 2t, a equals 2. Then the next part will be the sine of 2t, and don't forget the minus a half. So minus 1/2 the sine of 2t. Okay, so that's this next part. Then this s minus, it's set up as s minus a over s minus a squared plus k squared. That would correspond to e to the at cosine kt. So here, k equals 4 and a equals 2. So it's going to be e to the 2t cosine 4t. So this is minus, because of that minus, e to the 2t cosine 4t. And then this last piece, again, if you had the table, would be the same thing but for sine. So 3/4 e to the 2t sine of 4t. And we're done. Wow. Okay, good, good. It feels like we should be done. We definitely put in a lot of work on this one. So yeah, let's let's be happy we got to the end of that problem. But we're not to the end of the exam, right? Because that's number 5, which means we still have number 6 to go. Okay, so our last one. Let's hope this one's a little bit of a cool down. Solve the following ODE, so ordinary differential equation, with initial values using Laplace transforms. Well, of course, if you use Laplace transforms, you have to have initial values. It's built into it. All right, so y double prime plus 4y prime plus 4y equals 1, and y of 0 equals 0, y prime of 0 equals 0. Now, if you look at our table, and I'm going to, you'll notice we know how to handle second derivatives and first derivatives. Now, in the second derivatives and first derivatives, you have these pieces, the x is 0, x prime is 0, and the x is 0 here. That's where the initial values come in. So the initial values come in at the start of Laplace transform problems. But in our case, the wonderful thing, the glorious thing about this problem is our initial values are zeros. And so that's the best we could hope for. And so we can say, okay, fantastic. So we're going to get a lot of zeros showing up. So gone, gone, gone. So x double prime becomes s squared. X prime becomes s, x of s. So taking the Laplace transform, so get the Laplace transform, y double prime. Now you might say, oh, wait a second. You were just using a second ago, you were using x's, and this problem uses y's. Is that going to cause us any problem? No, it's just symbols. We can change it. We can change x's to y's. No worries. No worries. All right. This isn't genetics. Genetics, if you change x to y, yeah, that can make a big difference. But in math, that's just a symbol. No worries. All right, so s squared y of s. Then the next piece will be plus 4, and we're going to have s y of s plus 4 y of s equals, all right, Laplace transform of 1. Okay, well, good news. It's the first thing on our table. Ha ha ha. Okay, so it's 1 over s. All right, good. 1 over s. Okay, and the other pieces here that normally show up, remember those are gone because of our initial conditions. So we have s squared plus 4s plus 4 times y of s is equal to 1 over s. Or we can say that y of s, and notice that this is s plus 2 squared, is 1 over s times s plus 2 squared. All right. So we've kind of, in the process of solving a differential equation with Laplace transforms, we're at the halfway mark. You take the Laplace transform of both sides, you solve for y of s. And now you need to start sort of finishing up. And the finishing up says, time for us to pull apart. And pulling apart here means we're setting ourselves up for inverse Laplace transforms, starting with partial fractions. So we recognize that this would look like a over s plus b over s plus 2 plus c over s plus 2 quantity squared. And we need to solve for a, b, c. Clear denominators, and we have that a times s plus 2 squared plus b times s plus 2 plus c times s equals 1. Now, we could solve by expanding out and getting coefficients, but in this case, we can actually get a lot of values by just plugging in numbers. So, for instance, if you plug in s equals 0, we get that 4a is going to equal 1, because those terms go away. Okay, so that tells us that a needs to be 1/4. If we plug in s equals minus 2, then the first two terms drop away. And we see that minus 2c equals 1. So c is minus 1/2. And now we've got 2 out of 3. This is so much better than the last time we talked about partial fractions on this test. We like these kinds of partial fractions. Yeah, we love linear terms. They're our friends. Okay, so how do we get the last one? Well, you just pick a value. Any value you can do. How about minus 1? Now you might say, why are you picking minus 1? It's kind of halfway between 0 and minus 2, right? Also, minus 1 plus 2 is a really nice number to work with. So if we pick s equals minus 1, we'll get minus 1 squared, which is 1, so we'll get a. And here we'll get minus 1 times positive 1. So minus b. And then here we'll get minus c. And that has to equal to 1. But now we say, well, hey, we know some of these values. So we get 1/4 and minus b. And here, minus minus makes plus 1/2 equals 1. Well, 1/4 plus 1/2 is 3/4. Subtract. That tells us that minus b equals 1/4. So b is minus 1/4. All right. So we're a lot of the way there. Now updating, we can say the following. So y of s is equal to, well, we have our a, which we'll write this as 1/4, 1 over s, plus our b, minus 1/4, 1 over s plus 2, plus our c, which is minus 1/2, 1 over s plus 2 squared. All right. And now we ask ourselves, how do these things map? Well, y of s, that's pretty straightforward. That goes to y of t equals 1/4. 1 over s we've seen before. And I know we've seen it before because when I grab my table, the 1 over s is highlighted. It equals 1. So 1/4 times 1. Okay. 1 over s plus 2. Well, let's see. Is that on our table? It looks a lot like 1 over s minus a. Okay. So where a would be minus 2. So that would be 1 over s plus 2 would be e to the minus 2t. So minus 1/4 e to the minus 2t. All right, so we used that term there. And our last one is 1 over s plus 2 squared. Hey, check this out right there. So that would be 1 over s plus 2 squared. If a is minus 2, that would become t e to the minus 2t. So this would become minus 1/2 t e to the minus 2t. So again, the 1 over s is the 1 over s plus 2, e to the minus 2t, 1 over s plus 2 squared, t e to the minus 2t. And now, what do? The answer is we box it because we're done. Oh, wow. That was quite a workout. You know, I got to be honest with you. That was more intense than I thought when I sat down. I was just like, we're just going to have a fun 45 minutes of doing some problems. And, well, there were some definite challenges on this practice exam. Again, please let me emphasize, don't panic. This practice exam is significantly harder than the real exam. And I know when you see like an exam like this, you might get disheartened, be like, I don't know if I can make it. You totally can. You totally can. The reason we give you challenging problems is not to try to dishearten you too much, but rather we want you to sort of build up your mathematical muscles. And so once you get on the test, you'll do great. All right, keep practicing. I believe in you, and I'll see you again. Bye.